Semantic and geometric modeling with neural message passing and 3D scene graphs for hierarchical mechanical search. We address the problem of enabling agents to search for an object specified with natural language within an indoor environment such as homes. In our problem formulation, the agent needs to select a sequence of locations containing objects to look in. For instance, when searching for a red mug, it could first choose to search in the kitchen, followed by searching in the kitchen closet, and lastly in the middle shelf, at which point it also needs to decide on which occluding objects to move out of the way to make the target object visible. We assume an object detector allows it to reason about the mostly unoccluded objects to do this. We represent these sets of options with a 3D scene graph, which encodes the hierarchical set of locations the agent can visit as nodes we call containers. We assume the scene graph already has information about the environment's containers at the start of the search. While selecting containers to search, the agent needs to take multiple levels of information into account. For instance, if there's a closet in the bedroom, it will contain different items from the closet in the kitchen. Nodes representing objects are added dynamically when the container that has the objects is first searched. Both when selecting containers to search in and objects to move out of the way, the agent needs to take into account both their semantic and geometric properties with relation to a target object. We present a novel neural network architecture that enables reasoning about multiple layers in the 3D scene graph, as well as both semantic and geometric properties of nodes to decide on containers to search and objects to move out of the way. This neural network works as follows. For a given parent node, P, which corresponds to a container in the environment, we first combine its known geometric and semantic information into a feature vector Fp. We also create feature vectors for each child node, which corresponds to containers within the parent container or objects within the container. The objective of our model is to fuse information about the parent and children and reason about both jointly to decide whether the parent is a promising location to look in, which it does via neural message passing mechanism that creates new parent and child vectors with fused information. After this is done, the feature vector representing the target object Ft is fused with a new Fp vector and a classifier strain to output a probability of how likely that node is to contain or occlude the target object. To train and evaluate this approach, we present a procedural generation method to create a large number of synthetic but plausible scene graphs that have dense placements of semantically related objects on shelves. An example of our method is as follows. Given the target of canned tomatoes and cucumbers, the agent first needs to select among the possible rooms. Once it selects the kitchen using our neural network, it needs to decide among the possible containers within the kitchen. It then selects the fridge and looks on the lower shelf. Since the target object is not visible, it now needs to select objects to move out of the way. Our neural network enables it to correctly choose the semantically relevant objects and make the target object visible. Compared to several baselines, our method is best able to find a target object in a minimal number of actions on average, where searching within a container or moving an object are counted as actions.